Okay, welcome to Chapter 15 on air pollution and stratospheric ozone depletion. We're going to try to make this rather quick and get through this in just a video or two. So here we go. We're getting towards the end of the year. This is rather exciting. Okay, so moving on. Air pollution is any chemical, particulate matter, or microorganism added to the atmosphere that causes harm to plants, animals, ecosystem, buildings, or humans. So pretty much anything that's added that harms it would be considered pollution. Pollution comes from a variety of sources. Some of the major air pollutants you need to know: sulfur dioxide, which is involved, of course, in acid deposition; nitrogen oxides, which there's quite a few. There's nitrogen oxide, there's nitrogen dioxide, and there's nitrous oxide, all of which have different components with acid deposition and smog, and we'll talk more about those as we carry on. Carbon oxides. Carbon dioxide actually isn't really considered a pollutant, but it is a greenhouse gas, and we'll talk about that in Chapter 19. And then of carbon monoxide is, of course, an indoor air pollution that is very harmful and can cause death. Particulate matter is particles, little pieces of ash and dust and different things. The smaller they are, usually the more toxic they are and the more able they are to get into your lungs, which is of course a bad thing. Volatile organic compounds, VOCs. This is anything with a very pungent odor and usually evaporates at room temperature. So things like gasoline, perfume, formaldehyde, acetone, nail polish remover, those kind of things. Something with a very strong smell and basically will vaporize, will dry out very quickly at room temperature. Ozone. Ozone in the troposphere is pollution. Ozone in the stratosphere, of course, is good. Ozone is primarily a secondary product or secondary pollutant formed during a reaction in the atmosphere, and it's of course involved in, photochemical smog. Then we have also lead and mercury. We've discussed lead and mercury before. They pop up here because they end up in water, because they end up in the air first. So lead and mercury is a bad thing. Lead primarily from old paint and stuff, and of course mercury primarily from coal burning power plants. Okay, so this is a diagram from your book showing kind of all these things, why they're bad, where they come from, that kind of thing. So sulfur dioxide comes primarily from coal, but also can come from gasoline or any of the other fossil fuels and their things. So make sure you run over this and you're comfortable with it. If you have any questions, please let me know, but I think this is pretty straightforward, so I'm going to move on. How did we get to Oh, I guess we did. Sorry, I'm going around because I can't believe I'm on slide 5 already. Okay, so slide 5 talks about where some of this stuff comes from. Sometimes our particulate matter is coming from natural sources like fires. I apologize, I keep yawning. Volcanic eruptions, that kind of thing. If we're driving down a dirt road, you can make dust. A lot of construction makes dust. Fossil fuel burning can make ash. PM is the abbreviation we use for particulate matter. If the particulate's greater in size than about 10 microns, it's usually caught up in the mucus in our nose and throat and doesn't make it to our lungs. If it's between 2.5 and 10 microns, it does get into our lungs, but most of the time those usually end up being not things that are too toxic. But for some reason, I'm really sorry, all of a sudden I'm yawning. The really small ones, the particulate matter that's less than 2.5 microns is often toxic and of course makes it easily into our lungs, so that can cause huge problems. So you'll see that they're written as PM 2.5 or PM 10 to show the size. Okay, so when we talked about water pollution, we talked about point source and non-point source. When we talk about air pollution, we have primary pollutants and secondary pollutants. Primary pollutants are actually the pollutants we release from the smokestack, the exhaust pipe of your car, ooh, there's a typo, and natural emissions like volcanic eruptions and stuff. So carbon monoxide, carbon dioxide, sulfur dioxide, nitrogen oxides, and particulate matter all examples of primary pollutants. On the other hand, we have secondary pollutants. Secondary pollutants are pollutants that arise from a reaction with sunlight, water, oxygen, or another chemical in the atmosphere. So we release sulfur dioxide. It reacts with water and oxygen in the atmosphere and makes sulfuric acid. So sulfuric acid, which is one of the main components that in acid deposition, it's a secondary product. We didn't release sulfuric acid. It was made in the atmosphere, and that's where we get our acid deposition from, or one of them. So things like ozone, sulfate, nitrate, those are secondary pollutants. Okay, so for some reason your book throws scrubbers in at this point. I don't really understand why, but let's go over it. This is a picture of a scrubber. A scrubber is basically an apparatus that washes the air. So as the dirty air enters the bottom and comes up, it's being basically doused with a mist of water. And that water actually allows particulate matter and sulfur dioxide often to be washed out of this, basically washing or scrubbing the air clean before it heads out into the atmosphere. And this is actually a great thing because it not only removes particulate matter, but it also can remove things like your sulfates. The nasty water is collected in the bottom and dealt with, but one of the best things we can do, of course, is not make pollution. If we're going to make it, then we don't want to release it. If we get to that point, once you release pollution, it becomes extremely costly to try to clean up. So we want to try not to do that. Okay, so some natural sources of air pollution are things like volcanoes, lightning. Lightning will actually make ozone, and nitrates, as we know, for the or fixed nitrogen, like we know from the nitrogen cycle, forest fires, and even plants. Plants can actually create VOCs. You know, flowers, when they have that pretty cement smell and stuff, those often are VOCs. And then, of course, we have anthropogenic sources. These are things we're making, we do. So like on-road vehicles, driving your vehicle, it can create dust and stuff. Our power plants are burning things and create things. Industrial processes and our industrial machinery and factories and all. And then, of course, waste disposal. A lot of times we, and we'll talk about this in the next chapter, how we deal with solid waste, but sometimes we incinerate it. So that can cause a lot of pollution. Okay, so here's some of the sources. Things like carbon monoxide come from our cars. It's very common. One way we try to deal with that is by having a catalytic converter on the car to actually try to reduce some of that. Your nitrogen oxides are, of course, also coming from your cars. That's another big pollutant coming from cars is nitrogen oxides, primarily nitrogen oxide and nitrogen dioxide. Then your sulfur is coming primarily from electricity generation. That is your coal-burning power plants. And then your particulate matter, road dust is the biggest one, but then there's a lot of other things that can create things. Anytime you burn anything, you're going to create some particulate matter of varying size. Okay, so let's get down into some of the nitty-gritty. One of the things you truly have to understand is photochemical smog. And so on the screen you'll see this is the reactions that we went over with regards to photochemical smog. Nitrogen dioxide reacts with sunlight and it basically breaks apart into nitrogen oxide and an oxygen molecule. The oxygen molecule then reacts with the oxygen atom reacts with an oxygen molecule in the atmosphere and makes ozone. And this is one of the ways we get tropospheric ozone. It's a secondary product, and it's harmful just on itself, but in the right conditions, it can actually create or be part of photochemical smog. So in the bottom half, that shows all the steps to photochemical smog. You have NO2 is broken apart into nitrogen oxide and an oxygen molecule. The oxygen molecule again reacts with oxygen, or oxygen atom reacts with the oxygen molecule, and sunlight drives this again, and it becomes ozone. Okay, then the nitrogen oxide can react with VOCs, your volatile organic compounds, and there's a ton of them, and it makes a photochemical oxidant. Again, this is a very large, vast group of chemicals. But basically, when you have your photochemical oxidant and your ozone in the atmosphere together, you get what we call photochemical smog. Photochemical smog is also referred to as brown smog. There's two other types of smog you should know about: sulfurous or industrial smog, which is more of a sulfur-based smog and is often seen in cities where there's a lot of industry that creates sulfur. And then, of course, gray smog or London smog is often just smoke and fog, where the term originally came from. Okay. One thing you do need to understand is that there's a situation that can often happen called thermal inversion. In thermal inversion, you end up with a warm layer of air sitting over a cold layer of air, and it basically works as a lid. So looking at the picture, the top picture is normal conditions, and again you can see that this city is surrounded by mountains. This often happens with cities surrounded by mountains because the mountains kind of work like a bowl, if you will, and so the warm air kind of comes in from over the mountains and can trap the colder air beneath. So on the bottom, again, you get that relatively warm air above a colder air below it, and that warm air works as basically a lid, trapping all that pollution being created in the city. So for a time, that pollution is trapped there, and that's going to decrease the air quality in the city, and often people would be advised maybe to stay indoors or not do a lot of physical activity where you're breathing hard. Okay, moving on to acid deposition. Two chemicals are responsible for acid deposition: sulfur dioxide and nitrogen oxides, primarily nitrogen dioxide, but the others can react too. Sulfur dioxide reacts with water and oxygen to make sulfuric acid, which is a secondary pollutant. Nitrogen oxides react with water and oxygen to make nitric acid, again, another secondary pollutant. I apologize, I can't, all of a sudden cannot stop yawning. Sulfur dioxide, again, primarily coming from coal-burning power plants. Nitrogen oxides primarily from cars. Sulfur dioxide and sulfuric acid is the big culprit when we talk about acid deposition, but nitric acid, of course, has issues too. So, okay, so acid deposition. We call it deposition now because we have wet deposition and dry deposition. Wet deposition is precipitation, acid precipitation, but dry is just the fact that there's liquid in the air that this is occurring. Okay, so what are the effects of acid deposition? It will lower the pH of lake waters because, and that can be out of the range of tolerance for animals, so that could decrease biodiversity. It can mobilize metals in soil. Low pH soils, metals like aluminum and stuff will become mobilized and be absorbed into water and into the plants, which can have a detrimental effect. And of course, it can react with structures made out of things like limestone and marble and basically dissolve them. Okay, so how do we prevent air pollution? We already talked about scrubbers. There's also things like catalytic converters, baghouse filters, and electrostatic precipitators. We can also burn coal in combination with it's called, what is it called? Something scrubber. Basically in combination with calcium carbonate, and it reacts with that and helps to reduce some of the carbon dioxide. So that's another thing. Catalytic converters are found in cars and reduce your nitrogen oxides and your carbon monoxide, but not entirely, but it helps reduce them. Okay, so this is a baghouse filter. The filter is basically open at the bottom. The air flows up through the bottom through the bag, which is just basically a fabric bag. It catches particulate matter and then on out. What's kind of interesting is every once in a while they shut it down and they jiggle this plate that all these filters are connected to, and that causes all the particulate matter to fall out, and it gets collected in the bottom in a hopper. And so it's kind of self-cleaning, if you will. So it has that little shaker mechanism to get rid of it. Again, removing particulate matter only. Then we have electrostatic precipitators. In this case, the dirty air comes in and particulate matter in the air gets charged. And then as it passes across and through plates that have the opposite charge, it will basically stick to them. So it sticks to them, and then that way we're cleaning the air again of particulate matter only. And then every once in a while they actually shut off the charge to the collection plates, and all the particulate matter falls in the bottom in the collection hopper. Okay, this is a review of the scrubber we just talked about a minute ago. Again, basically rinsing the air, if you will, or scrubbing it clean. Again, removes particulate matter, but also removes sulfur dioxide to some extent. Okay, stratospheric ozone. You know what? Let's go ahead and wrap this up, and you know what? Let's just make this one video. Let's just do that. Okay, stratospheric ozone. Talked about this not too long ago, actually in class today. Stratospheric ozone is up in the stratosphere, and it blocks UVC and UVB light, which is very good because those are detrimental to us. So what normally happens is UVC light hits an oxygen molecule. It breaks the oxygen molecule into two oxygen atoms. Then the oxygen atom can react with other oxygen molecules in the air and make ozone. So UVC radiation is actually creating the ozone. Then, on the other end, ozone is also being broken down. It can be broken down by both UVC and UVB light. So ozone reacts with either UVC or UVB light, and it's broken down into an oxygen molecule and an oxygen atom. Okay, so these two things, they're naturally going on. These are the reactions that block all of your UVC and most of your UVB light, but they're at a steady state. They're both happening at the same rate, so the overall amount of ozone in our ozone layer stays the same. It blocks UVC and UVB light, and we're all good. Okay, so that's the normal, and that's what's supposed to be happening there. What unfortunately has been happening is we have been releasing chemicals called CFCs, chlorofluorocarbons, and these CFCs make their way into the stratosphere, and they react with the ozone and UV light. So what happens is we release these CFCs in the troposphere, but they are able to get to the stratosphere. When they get to the stratosphere, the UVC light actually interacts with them and basically knocks off, if you will, a chlorine atom. And then that chlorine atom will react with ozone. And so it breaks down ozone and basically snatches an oxygen atom from ozone and makes O2. The problem is that in the presence of all the other free oxygen atoms in the ozone layer, the chlorine will easily give up that oxygen atom it snatched and go back to being chlorine and creating an oxygen molecule. The biggest problem is that chlorine atom is then able to go back and destroy another ozone molecule. Basically, chlorine can do this. One chlorine molecule can break up or destroy 100,000 ozone molecules before it basically leaves the stratosphere and goes up further. So it's very detrimental. Okay, to back up a little, oops, that's not backing up. That's backing up. We find CFCs in things like your refrigerant, your air conditioning, your propellants like in aerosol cans, like spray paint and hairspray, and we use it to create like foam insulation and styrofoam and stuff. So it's a very valuable tool, but it's doing a lot of detriment to our UV light. If the UV or the ozone layer continues to thin and more UV light is able to come through, then you're going to see increase in things like sunburns, skin cancer, cataracts, a decrease in photosynthesis because plants don't like it, and those kind of things. So it can be very detrimental. Of course, there's also the ozone holes, which aren't really holes, they're just extreme thinning that occurs in the late winter, early spring every year at the poles. And that occurs because the CFCs and chlorine have been captured in ice crystals over the winter, and then the ice crystals melt and basically release a mass of CFCs and chlorine and causes this thinning to occur because all of a sudden there's this huge breakdown of the ozone by the chlorine. Okay, I hope you don't have any questions. If you do, please feel free to ask in class. Okay, we only have one more slide, and so this is our last slide. Indoor air pollutants. We have talked about this in class. Many more developed or developing countries have a lot of issue with indoor air pollution because they use wood or charcoal or animal manure to cook and heat their homes, their huts, their issues. So that puts a lot of particulate matter and chemicals and carbon monoxide and stuff into their environment, which can be very harmful to them. Very, very harmful. We have something called asbestos. Asbestos is an insulation, naturally occurring fiber that little pieces can break off when it's disturbed and they're inhaled, and it can cause lung cancer. So it's very nasty. We only find it in old buildings. We haven't used it in a very, very, very long time. So, but it's still, you can run into asbestos in older homes. So asbestos now is not going to be harmful unless you actually disturb it. Carbon monoxide is created due to incomplete burning. So if something burns, anything that burns is not going to burn completely, and you can get carbon monoxide. First thing you're going to get is a slight headache, then you're going to feel tired, and then ultimately it can cause death. Again, carbon monoxide is only an issue in an indoor situation because it builds up in a high enough concentration to be an issue. Radon. Radon is a naturally occurring substance that occurs due to the decay of radioactive material in the ground. Radon poisoning only usually occurs in houses with basements or in areas that have a lot of the decay. What happens is there would be a crack in your basement foundation or in the wall of your basement, and it basically leaks into your home and accumulates over time. Nosebleeds, headaches, nobody feels good kind of thing. So you have to be careful about those. And of course, VOCs in their house. We think it's the new house smell, the new carpet smell, the new paint smell, but they are VOCs, and they can be harmful. They can cause problems and respiratory issues and stuff. So you want to be careful with those too. A lot of things like carpet and stuff are treated with formaldehyde, which is known to be a carcinogen. Well, that wraps up air pollution very quickly. I hope you read. This is short and sweet. If you have any questions, please, please, please ask. But there you go. Have a nice evening. Bye.